Okay, welcome back. So as we have been talking in the first video of this particular course, so we had a overview of basic concept of the sustainability. We looked at some of the energy demand issues. Now in this particular video we'll focus on materials, because as I said earlier, to make anything, like if you are an engineer, you know that even if you are a non-engineer, you know that too, that if you make anything you need material. So the foundation of the world economy, it's a foundation that underlines the world economy. It's just how people extract and use the full range of material that comes from the earth, and also how we return it to earth. So we need to return this material back to earth so that the future generation can use it. So the world at large, we use vast amount of material, and as our affluence is going up, as our population is going up, these amounts are also increasing. So we are using lots of material. If we make more and more factories, more and more production, more and more demand, and more material usage. We have to think about efficient use of those material. That's why we need better technology, and at the same time how to come up with the technology so that we can recycle these materials more, so that we don't have to extract. So again, materials are very important, and we'll look at how these materials are managed. Some of the examples of are wood, mineral, fuels, chemicals, agricultural plants, soil, rock, and all these are the different materials that we use. So if you look at the world usage of material, this graph is a bit old, but even if you look at the graph, it will probably keep on increasing. You will see even further increase in this graph kind of going up. Because the per capita material use, which is billions of short tons means around it's a 2,000 pounds. Since the graph was generated in US, they use pounds, and it's 2,000 pounds is short ton, which is around 900 kg, not 1000 kg. So it's per capita material use, but that's, don't worry too much about the unit here. But what I'm trying to say is the per capita material use is increasing over last several decades, and then things are even it actually going up and up with slightly, you see these dips. Dips are basically during the periods where we have some sort of industrial recession. Either there was a less demand. So if you look at if there is a new graph available now, you will probably see a dip around 2008, 2009, where we have a global recession, but otherwise on average things are just going up. The developed countries, if you look, say in US, you see more flat trajectory, because they have already kind of developed. Their demand is not going, their population is also not increasing at the rate at which we see the population being increased in the developing countries, especially in Asia and Africa. So there is a lot of demand. The message that I want to convey from this particular graph is there is a lot of demand. There is a material use is there, and it is needed for all industrial activity. And in the 20th century, in the last century, as you can see, there is for the different kind of material, construction material, industrial material, metals, non-renewable organics, agricultural and forestry products. So in terms of the area, the y-axis is the million tons, and the x-axis is our years from the last century, and the graph came from the USGS report. So if you look at, there was a other than the Great Depression, you see that there is a continuous Great Depression or oil crisis or recession. You see there is a trend of increase in demand, lot of demand in the agricultural sector, and then the industrial mineral, metals, and agricultural demand is there, but not that high. So but in construction, and again, if you think about an Indian context, we are the government of India is pushing for housing for all right now. We want housing for all by 2020 or 2022, some I don't remember the exact year, but in next 10 years we have to build lots and lots of houses if you really want the houses to be built. And for those houses to be built, we need lots of construction material. We don't have that much sand available. If you really want to make all those concrete houses, we need a lot of sand, a lot of cement. India doesn't have that much sand, so that what that means? That means that we need to really manage whatever the construction material we have in a more efficient way. And one of the aspect of that is how to recycle some of those construction material, how to take this construction waste and demolition waste and recycle them so that they become usable. And there we'll talk later on as well that we have to be careful in terms of the environmental risk out of that. Of course, we need to look at the structural property. At the same time, we need to look at the environmental aspect, and we can look at from a big picture life cycle perspective how these things really fit on. So these are so there is a lot of demand, and same thing you will see these demands. Most of you see the graph for US. For developing this, if you look at the developing countries graph for this, somebody if you look at after 2100, if somebody plots this graph for India, China, they will probably see something similar activity happening in India and China over this in this present century. We will probably more demand because we have more population in here. So material is the material use that you saw in the previous two figures. That does not include fuel. So fuel is separate. It does include material. It does not include material that does not enter the economy. For example, the mining overburden. We produce lots of mining overburden. These are called indirect material flow. The graphs what we had was the direct material flow. So it's estimated that industrialized country, it's around 100 pounds per person per day. That much amounts of material. 100 pounds, we are talking about nearly 45 kilogram. So 45 to 50 kilogram per person per day is what is needed material for developing all these different resources, different infrastructure activities. But at the same time, as I said earlier, materials are limited natural resource. So we need to focus on recycling of this material back into the economy. So here in the past 50 years, we have consumed more material than total material consumed by our human race since existence of the human race in this particular planet. So, and I'm pretty sure this next 50 years will have probably similar use of material if the material is available. It just for United States itself consumed 57% more materials in the year 2000 than in 1975. The global increase is even higher. If you look at China or India, you will see much more material usage because this is based on the base year of 75. So since in the early base years our material use was much less, we may even have more than 100% or 200% increase. In 1900s, 41% of the material used were renewable. So out of all the material used, 41% were renewable, that agricultural, fisheries, forestry products. By 1995, it came down to only 6%, and now probably it will be much less. So majority of materials today is being now consumed in developed and developing countries are non-renewable, so including metals, minerals, fossil fuel derived products, and this is and we rely on these minerals a lot, especially for some of these like for newer products like cell phones, flat screen monitors, paints, toothpaste. All these materials, they require nearly 20,000 kgs of around 10,000 to 12,000 kgs of non-fuel minerals per capita each year. That's around 25,000 pounds. So it's rapid rise in material use that is leading to a lot of environmental impact on habitat destruction, biodiversity loss, overly stressed fisheries, and desertification. So if you were wondering at the beginning of this lecture that why I'm talking about this material, because everything is related. When you are trying to go for this material, you are impacting environment. So this whole life cycle analysis aspect is sustainability. Life cycle analysis is related to, as I said earlier, among the three pillars of sustainability, life cycle focuses on the environmental aspect. So there is a social LCA, but that's a different. This particular life cycle, as we will discuss in this particular class, is mostly focused on environmental. And when you look at this environmental aspect of for any particular product or process, the use of material from this product and process is very important, which does lead to these kind of impact in terms of habitat destruction, biodiversity, and all that. So there is a projection that world population will grow 50% by 2050. So whatever we had with respect to 2000, in 50 years, world population will grow by 50%. Global economic activity will grow up by 500%. And that will lead to global energy and material use grow of 300%. So think about that. That's a big increase. And so if you look at some of the comments on the effect of material resource use on environment, there are some of the research institutes in US, Japan, Austria, Netherlands. What they have come up with a conclusion that unless we do a economic growth can be dramatically decoupled from resource use, which is you want to have economic growth, but not too much of the use of the resource. When we say too much use of the resource means too much of the newer resource. Whatever is the resource available, we can recycle, reuse within the system itself. So, if we can decouple it from resource use and as well as the waste generation, we will have a lot of pressure on environmental issues, and that will mean lots and lots of usage of life cycle analysis kind of tool. So, that is why LCA tool, a person if they know LCA from a job perspective, from their marketability perspective, for when you go for a job interview, many companies will have to do this kind of LCA exercise. If many companies have started doing it, those who are not, they have to do it. Even the government agencies are looking at doing LCA now. Many European legislation, and even in California and other places, they are forcing people to go for this kind of exercise. So, this will help you in your job if you go for if you have an understanding of this kind of exercise. So, looking at this material is when your material, how it travels. This is the flow of material in a system. So, if you go from the left to right, you start with the resource extraction, where material resource you extract the resource, and that is your mining. So, and there you need a lot of the arrows that you see on top. These arrows on top is telling you the input coming into the system, and these dotted arrows at the bottom you see the emissions coming out of the system, and in the middle those rectangular boxes telling you the different units, the different processes that is happening as part of the material flow, and in between you see some of the reuse, remanufacture, recycle, and at part of disposal, part of it goes to composting, may go to the landfill. So, if you start from the beginning, you have the resource extraction. From the resource extraction, you go to the material processing, which is most of your metallurgy friends will do that for you. Then you go for product design and manufacturing. That will be designed and manufactured, where most of the engineers come in picture. Then product is used, where all of us comes in picture. That product will be used. Then it will go to the disposal. It has to be collected, processed, recycled back, and part of it will probably needs to be disposed as well. So, for all of these units, of course, the transportation is involved from one process to another process, whether within the plant or sometime from one plant to another plant, and the dotted lines at the back gives you the emissions to air, water, and land. So, this whole concept is how the material flow. So, this is we have to watch this steps very closely to look at where among these different activities where we see most of the environmental impact, and we want to reduce those environmental impact. So, how we will find out where the most of the environmental impact is after doing the LCA exercise. So, there is a rate of looking at the global material consumption and the environmental impact associated with that. Rate of deforestation is happening at a very faster rate, 1 acre per second. Our half of world's tropical temperature forests are now gone. We don't see them. 75% of marine fisheries are now overfished, overfished or fished to the capacity. Our marine life is also getting affected by the plastic pollution, which we'll also talk about at some point in this class. The freshwater withdrawal has doubled between 1960s and 2000. If you think about an Indian context as well, wherever you go in India, our groundwater resource is getting depleted at a very alarming rate. First, if you had water at 30 feet, now you go up to 50, 60, 70 feet, you don't see water, and many of these rivers are not reaching ocean in dry season. That's Nile, even Ganges, Colorado River, Yellow River. During the dry season, you don't see them reaching the ocean. There is a habitat destruction contributed to species disappearance at the rate which is about 1,000 times faster than normal. One half of the agricultural land is dry region is suffering from some degree of deterioration and desertification. So, their agricultural productivity is going down because of the usage of a lot of chemical fertilizers and other causes associated with that. So, in terms of this, as you can see, there is a substantial environmental impact which is coming up because of this different activities that is happening as part of the industrial or agricultural activities. So, another problem we have is the concentration of most of these minerals in the mining. When you mine, like in your mining ore, say today if you are mining for certain metals, if you are getting 1 kg of the pure metal from 100 kg of those mineral ore, tomorrow, like few years down the line, a few decades down the line, you may have to mine 1,000 tons. So 1,000 tons will give you, like, sorry, 1 ton will give you 1 kg. So you need to mine more and more. So if you have to mine more, that means more environmental emissions. That means more energy usage, and more energy usage means more environmental emissions too, and more water usage. So there is a lot of these things are all interrelated. So the amount of materials that have to be mined and processed is increasing. That increases the environmental impact. Then we have a lot of persistent bioaccumulative toxic chemicals coming into the food chain. Between 1970s and 2004, those 33 decades, the greenhouse gas emissions increased by 70%. And this most of the global average temperature is going up because of the greenhouse gas, because of the anthropogenic sources, and that includes extraction, processing, use, and disposal. So if you look at if you examine materials management, if you look at like how we can make an impact, as how this LCA exercise will be useful. So if you look at the natural resource, you have to look at the natural resource policies. You look at the product life cycle policies, natural resource policies, product life cycle policies, or the waste management policies. All the three, this orange hexagon that you see, these policies can take into account some of this life cycle perspective, try to improve the recycle, encourage recycling, may give them some sort of incentive, maybe some tax benefit. So so that we can reuse the material. We can although sometimes it seems to be cheaper to just go for the virgin material than to recycle. But if you look at the long-term cost, if you look at the environmental cost, that's where this life cycle thinking comes in picture. Where you look at the long-term impact, you see that actually recycling comes out to be much cheaper. There will be some situations where recycle doesn't work very well, but most of the situation recycle comes to be much cheaper as opposed to putting them in a landfill or in a waste to energy plant. So once and then you have the ecological system, then you have a societal system, you have an industrial system, and these are all related. So if you have ecological system, renewable resource stock, non-renewable, finite media, you have energy sources. A societal, you have you make durable product, consumable product use, service use, energy usage. So there are industrial system. We have some products and service supply chain, energy production. Material is being harvested from ecological system, goes to industrial system. Industrial system is actually filling the demand of the societal system. So everything is kind of related to one another, and this whole picture shows you the framework for examining how the material is getting managed. And this is very important in terms of when we look at things from a systems perspective, rather than looking at just the ecological system separately, industrial separately, societal separately. What LCA exercise does, it helps us look at all the three systems in totality, so that we can make a better decision. So coming back to that particular graph, if you look at these emissions, the sketch, the material management approaches, you see that here for A, B, C, D, and E, F, where A to C is your material substitution. We can replace toxic and hazardous chemical with something safer one. We can use for cleaner technology, reduce toxic and hazardous property, redesign industrial process so that it's more so that it produces less waste. Reduction of greenhouse gas, material, we can go for material regulation, and then F part where you have mostly waste modification. You can do some treatment, waste containment, in situ waste treatment. So all these will come into picture, like how you can use some of these approaches. So whatever you learn from your analysis, you can apply over here. So that's what we are trying to say over here. So material at some point of time it becomes a waste, and then it goes to the waste management sector. So material management seeks the most productive use of resource, but when it is not useful anymore, it goes into the waste management sector. The waste management, the goal is to minimize and manage waste or pollutants. Material management, they broadly focus on impact and policies related to whole life cycle of the product, including upstream, use of using less material, using less environmental intensive material, making products more durable. So material management and the waste management is interchangeable these days. You can have it's whatever was the waste earlier, if we start recycling them, that becomes a recyclable material. So many places in the world, they don't call it waste management anymore. They call it resource and recovery management, or waste resource and recovery of materials. So, goal of material management is the overall long-term sustainability, while the goal of waste management is focused on managing a single set of environmental impact. So, both when we look at the material management, the waste management actually is part of that, and and that comes into the whole life cycle of this particular material that we are talking about. It's a broad concept. There are a lot of different countries and government and businesses are including different types of material policies. This in European Union has a sustainable materials management policy. Then we have sustainable production and consumption, that United Nations Environmental Program. Then United Nations Environmental Program, another sustainable resource management. Many times you hear 3 R, these days even 4 Rs and 5 Rs, which is reduce, reuse, recycle. Now they're talking about recovery. And Sounds Material Society, that's in Japan. In EPA and others, they call for design for environment. Then you hear the term green chemistry, lean manufacturing, supply chain management, eco-leveling, green procurement, zero waste. All these different concepts has the basic philosophy is the same. Basic philosophy is to have better use of material, produce less waste, so that less environmental impact. And LCA as a tool help us to quantify all those aspects. So, if you look at the life cycle material approach for packaging, which EPA, US EPA came up with, so you have your resource. This is your life cycle. The orange sketch that you see is kind of going through the life cycle aspect from cradle to grave. You start from resource extraction and then you go to end of life. Resource extraction, material processing, design, manufacture, distribution, retail, purchase and use, and your end of life. So, for all these, EPA is working with materials manufacturers and converters to reduce the environmental impact for in each of these process, to come up with a design for environment program, where they try to encourage companies to go for more cleaner production. EPA's climate leaders and green supply network program assist manufacturers with reducing their greenhouse and environmental impact. They are working with big companies like Walmart to improve the packaging, and even Amazon, and so that because the packaging waste is too much. They also have a vehicle policy now to reduce the vehicle emissions. And with a Sustainable Packaging Coalition, which is an organization, EPA is providing input to design the label to tell the consumers about end of life options, whether the packaging material can be recycled, whether it can be composted, or can it be put in a waste to energy plant. So, those kind of information is being provided to the consumer as well, so that they can manage it in a better way. So, this is so many organizations around the world. We don't see this much. A lot of activities in this line in India has not started recently, it didn't started much. But recently, last year, or I think early this year, the government has set up a what is known as the Indian Resource Panel. So, there is an Indian Resource Panel now, which will look on policies like this, where they will try to have better resource management in the country. So, we will also start calling it resource rather than the waste management. So, that is in terms of the material, and one of the material, or one of the other resource that goes into is the water, and we need lots of water, as you will see in subsequent lectures. That water is very, very important for any industrial activity. So, clean fresh water, it's suitable for agricultural industrial use, and it's satisfying the thrust. In developed world, it's a combined use is around 1,000 gallons per person per day, and that includes every activity of the country, like domestic, industrial, all the activities together. So, 1,000 gallons, 1 gallon is around 3.8 liters. So, you can think about around 3,800 liters per person per day. So, close to 4,000 liters per person per day. So, if you have a 40 liters bucket, we are talking about 10 buckets. So, around 10 buckets per person per day is what is being used. Then we have sources are coming from surface water and groundwater. Those are the major sources. Surface water, it does get renewed on relatively short time scale, but the groundwater, it takes a long time. So, what is happening in a country like India, what we are seeing right now, we are extracting our groundwater at a much faster rate than what the mother nature can replenish it, and whatever was the groundwater recharge places, those places have been now filled up and made, we have high rises apartments there. We are making more and more areas to be concrete, paved, so they are becoming like a impervious layer, and that is creating reduction in opportunity for groundwater recharge. So, those are the problem where we have a lot of although we are extracting too much, and on one hand we are extracting too much, and at the same time we are not replenishing. We have actually hindered the replenishment of those groundwater recharge. So largest use in globally, including India, is agricultural, then thermoelectric power plant, and public supply, and water withdrawal, that's the remove water from surface and groundwater. But if the water is not returned to the same reservoir, the water is referred to having been consumed. So water is lost as a steam or from a lake. So there are some videos out there. I will not play this video, but this particular I would encourage you to check out some of this video on how the different stuff is made, what are the sustainability stuff out of that. This particular website is called storyofstuff.com. They also have a YouTube site. You can possibly want to go and check them out from there, and you can see a lot of videos associated with water usage, material usage, and other aspect associated with like a big picture sustainability. So just to summarize, we'll have a couple of slides here on so what we have talked so far. What is the sustainability and what does it mean for engineers? So we have said that sustainability means meeting society's present needs without compromising the ability of future generation to meet their own needs. You saw that, and then humans are integral part of the natural world, and the nature has to be preserved for our future generation. And most of these places we try to go for this triple bottom line solution which is good for environment, good for economics, and good for society. And many times it's very difficult to find a solution which will be good for all three. So you have to kind of optimize it. You have to optimize a solution which can be used, and that's where you look at this whole life cycle or sustainability aspect, where you have the environmental protection and resource conservation, at the same time economic prosperity and social well-being. So this is all this kind of goes in picture. So the three pillars is our people, planet, and profit. So that's your social, environmental, economical. So that's your three, like fair practice for all people, does not exploit interests of separate parties based on money, status, or growth. Planet, that's the environmental management of renewable and non-renewable sources. Profit is financial benefit. That's the economic aspect of that. Engineers are part of the problem. We have created a lot of issues. We have created a lot of pollution. You hear about Delhi, Beijing all the time, all the excess, but we are also part of the integral solution. It's what we have to come up with the solution to design all these different environmental protection systems and come up with the products and processes which are more environmental friendly. So here you see some of the renewable energy and all that. So we cannot keep designing the things in the same old way. We have to start thinking differently. So from next video onwards, we'll start thinking that what are the things that we need to start thinking differently. That we'll start looking at in the second week. The first next video will talk about the water demand and all. But this is so with this we'll conclude this particular video, which is your second module for the week 1. And I'll again see you on for the third module. Thank you.